Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 43 states that suppose a neutrino is created and has an energy of 35 MeV. Part A, assuming the neutrino, like the photon, has no mass and travels at the speed of light, find the momentum of the neutrino, and B, determine the de Broglie wavelength of the neutrino. Okay, so two things to do here. We want to find the momentum. So we think our expression for momentum, we know traditionally, let's see this part right here. Traditionally, it's mass times velocity. But we're told here, the neutrino can be assumed to have no mass. So when you replace this mass term, if we think, well, if we know that energy in these situations is equivalent to mc squared, we can replace this, we can rearrange this to solve for mass and replace it in the equation here. So mass would simply be E over c squared. And it does say, however, in the question that it does travel at the speed of light. So the speed of light is traveling is c. So the expression for momentum can be replaced with E equals P over, P, the momentum equals E over C. Which we're given an energy, 35 MeV. But note, MeV is not a MKS unit, so we need to convert that to joules in order to, well, this is a reminder because our speed is 3.0 times 10 to the 8 meters per second. Meters per second is our MKS units, so we need to convert MeV to joules to match that. So that's what reminded me. I wouldn't necessarily remember right off the bat that we need to convert. So that's joules per MeV. And we find that calculating this, that the momentum to two significant digits is 1.9 times 10 to the negative 20, and double check our units would give our typical units of kilograms meters per second. Great, because remember a joule, think of energy. If I remember what the units of a joule is, I just think of what it is for kinetic energy, which is 1/2 mv squared. So that's kilograms times meters squared per second squared. So if we divide this term by what we have, meters per second, we are left with our traditional momentum units. So that's a good reminder that we do need joules there. So that's part A. Part B, the de Broglie wavelength. Remember, that's lambda is equivalent to the Planck's constant over the momentum. That was equation 29.6 in our book, if you want a refresher where this comes from. So Planck's constant, we know in terms of joules, or SI unit here, 6.63 times 10 to the negative 34 joule seconds, divided by our momentum we calculated in part A, 1.9 times 10 to the negative 20 kilograms meters per second. Gives us units, if we were to check again, based on above, we would find we do have units of meters, and simply it would be 3.5 times 10 to the negative 14 meters. 14, sorry, make it a little bigger. And there you go.